Hello, and welcome to Aggressive Physics. Today is day 39, and what we're going to discuss today is Newton's third law. Now, Newton's third law is apparent to many people from when they're younger because it's something that's a common expression in everyday life. And Newton's third law simply states that for every action, there is an equal and opposite reaction. So every time that there is a something that occurs, there is a counter force that occurs with it. For example, if I were to punch a wall, my fist would become in contact with the wall, and when I apply a force to the wall applies a force to my fist. So I can't just punch the wall and have no repercussions. In fact, if I punch a wall, there's a good chance that I'm going to break my hand. Of course, it depends on how thick the wall is. If I punch a foam wall, I'm probably safe. However, the force involved is equal for both of the two objects. Now, we've been discussing equilibrium, and the question may be, if there's a force to the right of 100 newtons and a force to the left of 100 newtons, don't they just cancel out? Isn't that a state of equilibrium? Well, the reality is it's not, because the forces are acting on different objects. And later when we talk about free body diagrams, we'll be able to draw those forces and show that one force is on object A, my fist, let's say, and one force is on object B, the wall in this example. And since the forces are on different objects, they're not canceling out. In fact, if that was the only force acting on each object, there would be a net force and therefore an acceleration. Now, of course, if I'm punching a wall, the acceleration wouldn't be all that great for the wall because the wall has such a huge mass. On the other hand, the acceleration on my fist would be quite sizable because my fist is much less massive than the wall. Now, a common example of this in terms of assessments is a question such as the following. If a car is driving along the highway and hits a bug with the windshield, which object experiences the greater force? Well, the answer to that question is simply that neither of the objects experience a greater force because each one of them experiences the same force. The difference between the windshield and the bug in terms of the effect of that force is significant. In fact, the bug will be pulverized and the windshield will probably have no lasting damage on it. But the force on the objects is equivalent. So what we have is a fancy term for the two objects that are involved. In the case of the bug versus the windshield, the bug and windshield are the two objects, and we call that an action-reaction pair. And you always have to have two objects involved. And when you're doing problems dealing with Newton's third law, what happens is the action-reaction pair is flipped for each of the terms for the action and then the reaction. For example, if the force is, let's just say, 5 newtons between them, so the bug experiences 5 newtons of force and the windshield experiences 5 newtons of force, what you would do is write out the action as the following. The bug experiences a 5 Newton force from the windshield in a direction, we'll say, forward in terms of the car's motion. And that, of course, is a frame of reference if you're the driver. On the other hand, the reaction to that would be the windshield is experiencing a 5 Newton force backwards from the bug. So if we were to put the bug and the windshield as the two objects, the bug affecting the windshield, the reaction would be the windshield affects the bug. Now, a classic conceptual question that's often asked is the following. If you take a book and you drop it near the Earth's surface, it will fall towards the Earth. And the reason it falls towards the Earth is because of the force due to gravity. The Earth's gravitational pull is pulling the book towards the center of the Earth until it hits the surface. Well, what the reaction to that is actually the Earth is being pulled up by the book. So the action and reaction pair in that example is the book and the Earth, and then the Earth and the book. And a lot of people have difficulty comprehending that because we see the book falling, we don't necessarily observe the force that the book has on the earth. So every time an object is dropped near the earth's surface, it will be actually pulling the earth upward. The difference is the value of the mass of each object is significantly different. In fact, the book is 1 or 2 kilograms, depending upon what type of book you have, but then the earth is approximately 5.98 times 10 to the 24 kilograms. So if you just have, 1 or 2, that's the ones place, and then we're talking about going out 24 zeros past the 5. So 5, 9, 8, and then 22 more zeros in terms of the kilograms of the earth. So the earth is quite massive. And in fact, you will not see the value of the acceleration of the earth. It can be calculated, though. In fact, if you were to calculate the force due to gravity on the book, you would take 1 or 2, let's just call it 1, kilogram, and multiply it by 9.8 meters per second squared. Remember, force is just mass times acceleration. So mass 1, acceleration 9.8 meters per second squared. We're not experiencing terminal velocity within the confines of a room. So the 9.8 is going to be consistent throughout the flight. And what will happen is you'd have a force of 9.8 newtons. Well, dividing that by 1, you find the acceleration of the book. And in fact, you can do that with any object near the Earth's surface. Divide the mass, into the force, and you should get 9.8. On the other hand, you'd have to take the force of 9.8 newtons and set it equal to ma for the Earth. Well, the m is 5.98 times 10 to the 24 kilograms. So if you divide 9.8 by 5.98 times 10 to the 24, you end up with a value of approximately 10 to the negative 25 meters per second squared. So the acceleration of the Earth upward is actually 0.00000, add 24 zeros, and then you have a couple of decimal, a couple of digits past that. But that is I guess we'll call it an insignificant acceleration. If you're talking about objects in space where there's no outside friction or anything like that, you could effectively have the objects meet in the middle over a long period of time. The force of objects, for example, the Earth being pulled by the sun due to its gravitational pull, the reason the Earth doesn't spiral into the sun is because it has inertia and it travels in a straight line away from the Earth, away from the sun. However, that force pulling inward causes the Earth's orbit to be effectively circular. Now, I understand that the Earth's orbit is truly elliptical, but in terms of just the inertia of the Earth wants to go straight forever, but then is constantly pulled around the sun. The moon is experiencing the same type of reaction to the Earth's pull. The Earth and the moon have a similar force of attraction. They have the same value for the force between them. However, the moon is going to orbit the Earth because it has such a small mass compared to the mass of the Earth. So objects that orbit each other do so because the mass of that one object is typically significantly smaller than the object that is the source of the orbit. So the Earth is the source, and then the moon in that case would be experiencing the orbit. On the other hand, the sun is significantly bigger than us. In fact, the sun's mass is around 10 to the 30 kilograms. So if we're 10 to the 24 and that's 10 to the 30, that's 6 zeros. That's 1,000,000 times more massive. In fact, about 1,000,000 Earths can fit inside the sun, which is a staggering value that's hard to comprehend or even envision. Now, in terms of action or reaction, we have a number of examples that we could typically use to denote different types of Newton's third law. A common one is the way that rockets work. When a rocket is being propelled towards the atmosphere and then ultimately into space, there is a plume of gas that is ejected out the bottom of the rocket. So when you ignite the rocket, what's going to happen is the gas is propelled down. So the action would be the gas is pushed downward by the rocket, And the reaction to that is that the rocket is then being pushed upward by the gas. If you've ever blown up a balloon before and then let it go before tying it, you'll see that the air is being ejected out the bottom of the balloon, and the balloon is pushed forward. So you're not pushing the balloon forward. In fact, the air moving out the back of the balloon where you blow it up is going to then propel the balloon forward. Unfortunately for balloons, the path of the balloon is going to be haphazard. So it's going to move in varying directions depending upon the shape of the balloon. So a rocket is built so that it's stable, so that it moves in a straight line. If there were no fins on it, it would end up, it would go in some random path, and often, it could injure people. Students often build model rockets and put rocket engines in them. And if they don't have proper fin placement or proper fins at all, the rocket can move in paths that are not typically acceptable. In fact, that's why we often have students hide behind barriers when we're launching rockets, so that if the fins do fall off or there's a malfunction, it doesn't fly towards us and end up hitting someone. Now, we could use this technology even if we wanted to, let's say, soup up a bicycle or a scooter or something like that. We could put a big rocket engine on the back, have the rocket launch. The gas is pushed sideways out the back of the rocket, and then the skateboard or the bicycle or whatever object that it's connected to would move in the opposite direction. So if it was backwards, it would move forward. Another example would be, let's say, a hammer and a nail. A hammer hits the nail. The nail is moved downward into the piece of wood or into a wall or something like that, and the hammer ends up stopping because of the force of the nail. A byproduct of that is some loss of energy, and the nail would actually heat up. So temperature increase could occur. The hammerhead could actually become warm to the touch. And also you'd hear the sound. That energy would be released during that collision as well, and some of the energy would be released in terms of sound. So you have different forms of the energy within the hammer being released, not just to move the nail downward, but into the atmosphere as heat or sound, and in some cases it could even be light or other types of energy. But typically thermal energy, which is heat energy, and sound energy are a common byproduct of collisions such as that. When someone walks, they're actually pushing the ground backwards. But since the ground doesn't move, the ground's reaction is to push someone forward. So when you are walking, you're never actually moving your body forward in terms of your foot. You're pushing back on the ground, and then the byproduct or the reaction to that is that the ground pushes you forward. When you climb a rope, you pull down on the rope. You don't actually climb the rope, you pull down on it, and the reaction is that the rope pushes you up. Same thing with climbing a ladder. As you climb a ladder, you pull down on the rungs, and the reaction is that the rungs push up on you. Another example would be if you're trying to walk from a boat or a canoe onto a dock. And this is an example because friction is typically less in water. So what could happen is you could push on the boat, and then the boat moves backwards, but it doesn't have enough friction or traction in this case to propel you forward. So you might push backwards, and if no one's holding onto the boat from the dock or it's not tied down, you could end up just falling down into the water. So when you go from a boat to the dock, you have to be careful to push downward as well as backwards. So you have two different directional forces, probably at an angle, which we would then need to resolve if we were going to calculate it, and you would move forward and up due to the motion of the foot. When people start races, often you'll have starting blocks, and that's so that you can push more horizontal in terms of your force, so that you have a better propulsion on that first move out of the blocks. When you have elementary school field days and you have relay races, a lot of times the person in the front of the relay race will push off from the leg of the person who's going to go next, and that gives them a better use of their motion. Because any of the motion going down or any of the force that you push down into the ground is effectively being wasted. It's just going to move you upward. You want as much of your force to go backwards so that the reaction is a forward motion from the ground. That's why you wear cleats during sports. The cleats will dig into the ground and allow you to push backwards better onto the ground so you can propel yourself forward. Effectively, it ends up being that the traction is increasing, so you're able to push backwards more effectively. Now, finally, I mentioned already punching a wall. If you were to punch someone or punch a wall, there is an action reaction from the fist and the wall, or the wall and the fist. Anytime two objects collide, the force on them is equal. The effect of that force may be different. And usually the smaller object experiences a greater acceleration because of Newton's second law, F equals ma, and that effect can be devastating if we're talking about the bug in the windshield, or it could be painful if you punch a wall or you punch a more massive object. That's why it's important to avoid collisions if you want to avoid injury. The forces are the same, so no matter what, you hit them just as hard as they hit you, but it can be that you experience a greater amount of pain. And in physics, we're not going to calculate the pain threshold. We're simply going to say that the forces are equal. So in terms of Newton's third law, the definition is for every action there is an equal and opposite reaction, and we need an action-reaction pair between the two. The forces are the same, the directions are opposite, and the objects that experience the force have to be two. Bug windshield, and then windshield bug, fist wall, and then wall fist. And then the more tricky example is if I drop a book in the Earth's gravitational field, the book is pulled down by the Earth, and the reaction is the Earth is pulled up by the book. Now that is Newton's third law of motion. Now, Newton's third law is action-reaction. So you have action-reaction. So what we have is a situation where, like the law states, every action has an equal and opposite reaction. So if you have a hand and you punch the wall, two things are going to happen. The wall is going to be punched, so there's going to be a force on the wall, to the right in this case, and then there's going to be a force that the wall exerts on the hand. So there's going to be a force to the left. Now, since these are equal and opposite, equal number, opposite direction, the common thought for many students when they're first looking at this is that these two forces cancel out and it's in equilibrium. That's not true. And the reason that's the case is because this backwards force is on the hand. So this is the force on the hand. And this force is on the wall. So in order to have equilibrium, you have to have all the forces cancel out on a single object. So that's the major difference between Newton's third law and equilibrium. An object can still be in equilibrium. However, it's not because of Newton's third law that the forces cancel out. Each force is acting on a separate object, and there's always going to be two objects involved. In this case, it's a hand and the wall. So the two objects are hand and wall. If we're talking about other situations, maybe we're talking about a hammer. Well, that's a terrible hammer, but it's got a claw. And a nail. The hammer is going to hit the nail, so there's a force on the nail. It's going to go down. And then there's going to be a force on the hammer, and that's going to be up. Now, the force on the hammer is why it stops. The force on the nail is why it drives into the board or the wall or whatever you're hammering the nail into. So it's important to realize that these two forces, although equal and opposite, they do not cancel out. They stay and they affect the objects because they're acting on two separate objects. So Newton's third law, every action has an equal and opposite reaction, is not an example of why equilibrium occurs. We could have other forces acting on these objects that will cancel them out, but the action-reaction does not cancel out and cause equilibrium because they're on two separate objects.